trained. So this was actually very fast. Token to token generation. It was indeed a diffusion based generation. Start building our tutorial script. So first thing first, as I recommend, is to let's put a check whether we have an enough amount of GPU memory available to us or not. So let's from Unsloth, let's import fast model and let's import torch. So let's check if we have enough GPU memory available. So there is an API .cuda is CAILABLE, and we can check if the free GPs. So we have something called torch.cuda.mem, I believe, mem get info, yes, okay, and we will get, oh, that was a good auto completion, and we will get the 0th value. Let's divide by 10 to the power 9, and we will say if, let's put a check, if free GP is less than, if your GPU does not have 50 gigs of RAM, and then you can't do this. I'm just putting this check so that a person knows like why they are facing the error, because this is a good suggestion. So did I made some mistake? See CUDA. For me there is no error. That means my machine is good enough. It has an 80 gigabits of GPU memory, and I'm using an A100 model. So next thing is we want to actually load, since now that we have this confirmation, we should actually go ahead and import our models. So here's what we have done is the fast model is the Unsloth universal loader, and it reads the checkpoints.json, sees the diffusion model type, and route to a transformer based diffusion path instead of the usual fused kernel autoregressive path. So here the -it is actually the instruction tuned variant that follows chat prompt style, and the base variant would need format training first, so which we don't want. It's a good for us. So let's define the type. Let's dot bf float 16. Yes, now there's one another. So bf float 16 has same exponential range as fp32, but it has a less mantissa. This, I hope this is what it is pronounced. It is standard for training stability on A100 because it's a native bf16. So fp16 would risk overflow in the loss gradient spike. This is what I have seen. And one important flag that we need is load in, because most of the Unsloth books have this, load in 4-bit equals to false. Doing this is important because we are deliberately turning off this bits and byte 4-bit quantization, and the 128 mixture of expert here are fused in the 3D tensor, one big number of expert input output parameter, so it's not a 128 linear module. So bits and byte cannot touch them. You would quantize the 6 gigabit backbone and still carry the 46 gigabyte of bf16 expert. So no memory win, and so added because it adds the dequant overhead, and then we just need to pass ed tokenizer, and that we have done the this process. And lastly is if we will follow the same notation as the Google, like they are mentioning tokenizer, so it's just aliasing here, naming alias. So because diffusion checkpoint ships a processor, which is tokenizer plus chat template plus diffusion specific encoding glue. Unsloth returns it in tokenizer slot. This alias will keep the code readable. And let's do also one thing. Let's measure the vocab size. So from model config, text config, this gets stored in the model.config. So because it's going to help us when we do the corruption step that samples random token IDs, which is going to be in between range 0 to vocab. And let's also try to get the canvas length of the model. The canvas length is let's also see, let's print them. Vocab EOC, vocab and canvas length is canvas length CAP. This is a good suggestion, and yeah, I think it's pretty much good. Let's try to run it. Okay, canvas length has an okay, I believe so. There's some error. Okay, name tokenizer is not defined. I believe. Okay, let's try to run this code. Okay, so in BF16 we are not loading the bits and byte, and it's going to take a couple of minutes. And make sure that you have with enough memory available. Just a step, because it's a bigger model. Maybe in future variation we will see some Gemma smaller variant as well, but for now this is something, but the process is going to be remain same that we are going to learn over here. And now meanwhile it's happening, let's go ahead and do the LoRa configuration. So once we have the model, we will use fast model get peft, and we will define the model. We pass the model that we have got from here into here, and we are going to define the rank, the scaling factor, and the use gradient checkpoint. I'll explain what this line is actually going to do. So basically this wrap our model with peft LoRa adapter. So per adapter weight, which is in the shape of D cross K, LoRa is going to learn, and the cross product, I believe it's inner product of B and A matrix, like so a bigger matrix get resolved into two smaller one, and let's say that A is a rank of R cross K and B is a rank of D cross R. So the effective weight would be W plus, the formula is something like this: W plus ALPHA alpha, the scaling vector, divided by rank into the dot product, and P, and in Python you can do this. This is where you are going to calculate the inner product. So the R is equals to 64, which goes here, is the adapter rank. You can say the capacity of updates. 64 is a very generous. Here the classification could likely work in 16 to 32 as well, but 64 is cheap relative weight for this model, since this is a very bigger model. So LoRa alpha is 128. It's the scaling numerator that you have seen over here, and this is common practice to have it. This value is good enough for us, and the important thing is this flag, use gradient checkpoint. Oh, meanwhile our model has been downloaded, and it has the vocab of this much, and the canvas is 256, as what I have explained in the whiteboard session of the tutorial part. So what I was saying, that here the checkpoint trades the compute of memory by rerunning forward during backward on an 80 gigabits card with patch size of 1 and 256 token canvas. Memory is not the constraint, so it keep it off for a speed. And so let's attach our LoRa adapter to the model, And let's do one thing. Let's try to see the GPU CPU usage meanwhile it's happening. If you can see, we have right now we are not using that much CPU memory. It has gone to the peak of 20 gigabits, this the RAM, but our GPU is now loaded. The 49 gigabits it has taken it, and during the training it is actually going to take more, and when it's loading in the GPU had spiked to 5%. So we are going to monitor them during our training session as well. So we can see it has attached the LoRa adapter, and or it has this much, I think it's in billion parameters, and then we are just training 0.5% of it. So this at this stage we have our model available to us. The only part remaining is to bring the data, how you are going to use which data. So it's going to be a classification problem. Now for the dataset I'm going to use simple CSV files. This is what usually our data gets stored somewhere in a CSV file, JSON file. Google has taken an example of Sudoku in their official notebook, which I really don't think most of the people will be able to make sense out of it. So I am going to use a simple data which has a conversation as the input, and their label is going to be a structured JSON, because this is where this model shines. So we are going to bring two CSV straight from the Poly AI's GitHub repository, and so we are going to use that. So let me bring all in the data. So here what we are doing, it has a 10,000 banking query, and this is the GitHub repository where this banking data is present, and based on the customer query we are trying to classify them on some intent, like what is the request is actually. So it has bought the data for us, and then let's try to read some of the intent into let's try to print. There are 77 intents. See, refund not showing up, active card, age limit. So they have categorized on 77 intent names based on the user, their query, and we are going to store this is going to be a fixed list. So once this is done, then let's define a prompt for our model. This is going to be the prompt template. We are going to ask model classify this banking customer into exactly one intent, and we are going to share it all of the intents, all of the 77, that see this is something which is available to you, and you have to reply in a JSON the intent and the intent name from among the list, and this is going the message. Then we are going to pass the user message. So what is happening here, there is 3 decision design that we are taking in this string. All 77 intents are embedded into the prompt has no canvas limit, so remember that, only output 2. So we spend prompt token to constrain the output space to make the fine-tune robust to the label name recall. It's where this is something that when I was working with it, I found it improves the model's performance. If it allows you, then I would recommend you can pass all of them into the prompt, and only to JSON is very important. You'll need to mention them, and once it is done, then we can define a format function which is it takes the intent and text, and then it's going to put them in the message and the label. So convert each rows to a chat message format. So this is what we will actually do. We'll take the text and intent, and then we are going return the, so we'll take the row messages, we'll format the prompt, and then the intent is the content, and the label is going to be, this is the format that you have to bring your data. So let's try to run this cell. Our prompt is ready, and then our function is also ready, and then we can start preparing our data. We'll just convert each row and the training row, the evaluation row, and we are not going to use all of the training point. Let's just keep 3000 examples so that this tutorial is not that big, and let's try to see some of the input samples. So if you see, this is the prompt. Classify this into one intent, and the allowed intent list, you can see all of them are present over here. Let's do one thing, let's try to see everything for this. From this, reply with the JSON, the intent name only. You can see all of the intent name are present over here. And so this is the message that a user, the ATM did not give me what I asked, but my balance says it did. My intent goes to wrong amount of cash received. So look at this data. This is real humans. The typos, the fragments, frustration, and that stuff is what your production system actually sees. So that's what a real data beats the synthetic tutorials. So for now we'll proceed with further step. If you want to plug in your own dataset, you can very well do the same way. You can see that these are pandas data frame. Eventually you want to use the two rows. So using the two row function, we take the text and its category, zip them, and then passed the user message and the row into this format. So this is something you have to develop based on your data, which columns that you are going to select as the input to the model, and what is it going to predict. So that's very basic thing. I would expect everyone to be able to do that. And so now coming to the training, we have loaded our data, we have our model, and this is where the video stop being a normal fine-tuning tutorial, because now if you have ever used Unsloth, you cannot use a SFTTrainer here. There is no next token prediction. The training objective is diffusion objective, and it's actually beautiful. So what we have to do is we have to now corrupt our input, and the corruption process that we have that we tried to build our intuition in the introduction session. So what we are going to take a clean target, we are going to pad it into the 256 tokens, then corrupt it. Every token gets replaced by a random token with a probability t. So that's something we defined. T is sampled fresh each step, anywhere from 10% noise to 100%, and then we hand the model prompt plus this ventilized canvas and say reconstruct the original with the cross-entropy loss on real token, and we are going to ignore the padding. So now let's define, first of all, let's get the model's actual end of sequence token, because we cannot just use any random, it's going to cause some problem. So from model generation config end of sequence token ID or 1, this is, you can use 1 as well if we will not be able to use it. And then so the end of sequence ID can be none as well. So in that case we can fall back to 1, bare integer, or a list of ID Gemma friendly model often register several stop token. So normalize it to 1 integer. So end of sequence is appended at every target, so model learns where the answer ends, and it's going to be inside our 256 slot canvas. Now we have to start unwrapping the tokenizer, and these are the two lines which is going to help us. Here let me explain what is we are doing. So the pad fallback for E, so if E of end of sequence is undefined, the fine here, because we are going to pad position are masked out of the loss anyways, so then the ID just is going to just fill the space. This is just something we have to ensure while we are working. And once this is done, then we are going to define our function, which is going to build an example of noise. So this function is quite a bit important because for every row we will first apply the chat prompt template. So what is actually happening, the user message we will convert into the chat prompt template, the role maker, exact format of instruction tuning, what checkpoint expect, and what we have added one flag here, which this add generation prompt true, which is going to append the assistant turn starts here, this token. Without it, the model is positioned in the mid user turn, and then we are going to strip the batch dimension. Now note what's not template. The target is not the template. The assistant content is encoded raw on the next line because it goes on the canvas, not in the prompt sequence. So here the token encode message content, what we are doing, the raw target plus explicit end of sequence terminator. Now this line says that if the n length is greater than n is greater than the canvas length, so we have to hard skip over the length target, but in our data it's not going to come closer. Now this line is very important. So x0 variable is actually a diffusion notation for clean signal at the noise time t is equals to 0, the very initial step. The target padded are exactly 256. Remember that. Fixed sites tensors keep every training step shape identical, also dynamo friendly so that there's no recompile. And then the next line is the masking. So loss mask, which is we have set to be true on n real position, the context plus end of sequence, and it is going to be false on the padding. So this is what is happening here. The model is graded only on the real token, not on the padded one. And then finally we append the prompt ID, the initial diffusion noiseless step, we can say. So pre-tokenizing everything once upfront, and tokenizer never repeat inside the hot training loop. And let's build this function, no error. Now let's try to see one example of what is actually we are seeing, and let's try to print. Let's take an usable example that we can use, and let's see how many examples do we have actually. So the training is going to build, and then let's get this cell. After that we will actually, okay, so looks like it's not printing. Let's try to run it over here. Yeah, so about 3000 example, all of, so we haven't rejected any one of them, so that's good thing, because generally the user queries are small here, but depending upon the use cases it can be bigger as well for other people. Now the important piece of code is the training loop itself. Let me bring the code over here, and I can see everything is here. Now let me explain you the exactly the important lines of this code. So the first one is this is what finds the device of the first materialized parameter. So if the accelerate, offload any weight, those parameter reports device meta, so which is the shape only placeholder. So sending the input tensor to meta crashes. the generator expansion skip meta parameter, and the fallback that handles no GPU edges. So this is something that we are setting. It, we have to handle them so that there is no crash because of the metadata. Now these constant, let's talk about them. So what we are saying, the steps is 500. This is the optimizer steps multiplied by 4 accumulated micro batches, so roughly 2/3 of the epoch over 3000 rows. So this is for the proof of concept scaling, and generally this is how you should do training. Start on a smaller batch and see if it will be able to scale. The learning rate is 10 to the power minus 4, which is good. And let's define the minimum corruption level. We want every sample to be at least 10% corrupted. And then what we are saying that model.config that use cache keeps the cache path enabled for model internals. And because in AR training you would disable the KV cache, the diffusion path manage its own caching semantic and leaves no that's important. And now the optimizer step, we are going to use the Adam. So what we are saying, optimize over trainable parameters only, just the LoRa adapter, everything else is frozen. The model parameter, p required gradient, learning rate we are setting, and this is why optimizer state is in megabytes, not the full 200 gigabytes. Full model Adam W would need about the beta 2, roughly we have set to be 0.95. The shorter second moment memory, the modern LLM training choice says for noisy gradient. So let's set the weight decay to 0. LoRa delta starts as 0 and stays small. Decaying adds nothing here. Now we have defined the scheduler, the learning scheduler. So it's a linear warm up over first 3% of the steps up to this is a cosine decay to almost 0. The warm up protects the freshly initialized adapter from the larger early gradient. So what cosine is actually cosine decay actually settles at the end of the training. And then we have our corrupt function. This is the heart of the method. Each examples get freshly sampled from the noise between 10% to 100%. So across the training model sees every regime from a few error to generate a pure noise. That spectrum is what makes multi-step inference refinement possible. Now if you see, we are making a clone is required because x0 is the cached clean tensor, and it is going to be reused across the epoch. So in place corruption without cloning would permanently is going to vandalize our training dataset. So now here this is something we have talked about in the mathematical explanation. This is pre-position Bernoulli mask that then replace the mask position with uniform random vocabulary IDs. Note here the random tokens, not special mask token. So this is the uniform noise discrete diffusion formulation. The model must learn to detect the corruption, not just fill the masked blanket. So this is something Google has newly introduced, and they have mentioned that in their paper. It's very something I would say this is the real heart of. We are able to see the transformer models are able to perform well. Now generating 256 random IDs. So what we are doing is we can waste few IDs but keep one vector ready. So now this is the training loop, and let me define what is here happening. This this is actually the diffusion's forward signature, because SFTTrainer is impossible here. So the input IDs, the prompt, conditioning, context, unsqueezed, and we are just adding a patch dimension. The canvas IDs, which is the corrupted target block, what model must repair, and the self-containing logic is something we have set to none, standard for single pass training. This is now for here. Once the vocab distribution per canvas position, all 256 predictions simultaneously, full block reconstruction, not next prediction. This is what we are setting here. And then it's also going to upcast the BF16 to FV32 before softmax or cross-entropy. That makes log sum, because to maintain the accuracies. And then the loss function is just calculating the cross-entropy loss, and then we are doing the backward pass that is going to update the weights and biases of the LoRa adapter. So with that, we are ready, and let's log every 20 steps to see how much progress we have done. It's going to take some time, let's see, and we can meanwhile let's monitor our usage. You should start to see GPU percentage, CPU percentage getting up. Now you can see it's 20% utilizing, memory is getting used, and now the GPU must have crossed 50 gigabits, 57 gigabits of memory. So that's why we have put that condition, like you cannot go beyond. I mean, you need a higher GPU for this for training this model. Even if you are training the just 0.5% of the trainable parameters. So once this step is done, we are going to call for the evaluation. That's which is just the same thing that we have done. We are just going to do the generation, and then we are just going to measure the evaluation rate, and then we'll check the intent accuracy, how much we are getting. So 20 step has been passed, and it takes 76 seconds for 20 steps. So which means in 10 minutes it's going to do roughly 200 steps. So I'll fast forward it, and maybe for the video I will try to reduce the steps to few hundred. I think that will make sense. Let's try running only hundreds so that it's done in. Let's try to stop it, and then let's run it again so that it's quickly done. It's going to scale more, but I believe waiting 3 to 4 minutes would be good for this model, because it's not a very difficult. Once this is done, we will do evaluation, and then we are going to we are going to make an inference of the trained model, and let's see how it does over there. So let's wait for 5 minutes. We'll get back. Alright, so model has trained, and the loss is actually in 100 steps. I can see it has initially from 0.30 to it has dropped 0.0052, and you can run the evaluation. It's also going to take about 3 minutes, but I would like to first see the model working. Okay, so we need to specify the generate function, and then we can call it. We are giving it 64 steps, and it was able to do the generation. So let's also do the evaluation. So it's working. Like we have this was actually very fast. This was not token to token generation. It was indeed a diffusion based generation, and I transferred money 2 days ago, still haven't received to my account, and it is correct intent, transferred, not received by the recipient. So this is how you can develop your own model. And if you can see in the step 1 itself, the model has a good output generation. 98% is good, considering we have only trained it on 100 step, and it has an accuracy 53%. If I would have made it multiple epochs, then we can have a very high accuracy. That's a tunable parameter depending upon your use case. You can play with that number, how many steps of training that you want, and you can plug your own data set the way I have did it. Make sure that the format is like this, and if you can see the GPU usage, it's peaking at 64 gigabits, and it's going about 50% of compute. It's a compute bound operations, and CPUs is not that much used, and the RAM is getting used about 4 gigabits. So that's interesting, and I believe this tutorial was although a bit lengthy, but I hope that was helpful. I am going to attach this notebook at the description of this tutorial. You can follow it along, and thank you so much for watching till this point.